Okay, we want to find the places where the local maximum and minimum occurs now. Okay, maxima is just the plural of maximum, and minima is the plural for minimum. Okay, suppose that x equal to c is a critical point, and we know that the derivative is 0 there. Okay, so that's telling us that the tangent line is horizontal. Okay, and the derivative exists, so it's not going to be a sharp corner. Okay, so what we have then, if we have that the tangent line's horizontal here, and we know that f prime is actually 0 here at c, to the left or the right, it's either the derivative is either positive or negative. If the derivative is negative to the left and then positive to the right, then we're going to have that the function's decreasing to the left, increasing to the right, and that means that the function has to have a local minimum at c. Okay, again, we're looking at our critical point c here, and let's say that now we know that the derivative is positive to the right, to the left, and the derivative is negative to the right. Well, that means that the function had to be increasing to the left of c, decreasing to the right of c, so that we'd have to have a local maximum at x equals c. Okay. Now, looking at this picture, I want to look at these A, C1, C2, and so on up to B, and look at each point and see what's going on. First off, at x equal to A, we see we have a local minimum, an absolute minimum. It's not local because it's at an endpoint. Local ones can't be at an endpoint, but it is the lowest y value across the board. So we have an absolute minimum at A. Okay, so now we see our function is increasing. Okay, so in this interval, we see that our derivative is going to be positive. So the derivative is positive if the function's increasing. Okay, now at C1, we see that tangent line would be horizontal. So if the tangent line's horizontal, we know that the derivative is 0 there. Okay, now notice though, to the right of that, our derivative is positive still. We have the function still increasing. So it was increasing to the left and still increasing to the right, which means there isn't, even though we had a derivative of 0 at C1, there is no extremum there. No maximum or minimum. Okay, so if it's positive on one side and positive on the other side of a point C1, it's not a maximum or minimum. Okay, so now the function's still going up. Now it's starting to come back down. So in the interval from C1 to C2, it's decreasing. So we've got that the function has a positive derivative to the left, a negative derivative to the right because it's decreasing. And so if it's increasing and then goes to decreasing, and this is a place where there is a derivative of 0, we have to have a local maximum. Okay. Now at the next point, notice to the left of C3 here, the function's falling. That means the derivative is negative. Now it's going to rise on the other side. That means that the derivative was positive to the right of C3. If the derivative goes from negative to positive, falling to rising, it's got to have a local minimum at C3. Okay, now notice at the next point, the function's rising, comes to a sharp corner, but now it starts falling. Well, that tells me the derivative is changing. It was positive to the left. Now it's going to be negative to the right since the function's graph is falling. So I'm going to have a maximum at that point. Now, it doesn't have a derivative that's 0. We actually don't have a derivative at all at this point because of the sharp corner. So the derivative does not exist. But we still have an absolute maximum there because it is the highest point. So we have the absolute maximum at that point. Okay, so now if the function's falling to the right of C4, it's going to get to C4, kind of level off, and then it's going to keep falling. So we've got that the derivative is negative to the left, negative to the right, since it's still falling. So the function's decreasing both to the left and the right. So at C5, we don't have a maximum or a minimum there. So there's no extremum there, but we do still have a derivative of 0 at that point. The tangent line is still horizontal. Okay, and then finally the graph ends by falling down until it gets to the point where x is equal to b. So we have our derivative is negative there, and we have no local maximum or minimum at b, and there's no absolute minimum since we had it at x equal to a, we had actually a lower point. Okay, so look at all the local maximums and minimums, and look at the absolute maximum minimum. Look at where the derivatives are positive or the derivatives are negative, and get that with correlated with the graph. Okay, so what we want to do is we want to find the maximum minimums, and we're going to use what's called the first derivative test to do that. Suppose f is a function that's continuous on an interval, and c is a critical point. So what we're going to do is we're going to find the critical points, and then we're going to test each one of them individually. Okay, so now, if the derivative changes signs from positive to negative, that means that we had the derivative is positive, and then it's going to go to where the derivative is negative on the other side of c. That meant that it was rising to the left, falling to the right. We've got to have a local maximum at c. Okay, so now if f changes signs from negative to positive after you pass c, so here's our c, the derivative is going to be negative to one side, so f of prime is going to be less than 0, and then it's going to be greater than 0 on the other side. So what we have in our graph then is the function's falling to the left if the derivative is negative, and then it's rising to the right since the derivative is positive, and we're going to have a local a minimum at x equals c. Now, if it doesn't change sign at all, so if you have that the derivative is positive on one side and positive on the other side, that means it's rising, comes up to a 0, and then it's going to continue to rise. Or if it's negative on one side and then negative on the other side, that means it's falling, comes to kind of a level spot, and then it continues to fall. Then we don't have any local extreme values there. So in other words, it has to have opposite signs from either positive to negative or negative to positive for us to have a local max or a minimum at a value c, at a critical point. Okay, so now using our first derivative test, find the intervals first where the function's increasing, decreasing. We do that by getting the derivative, finding where it's 0, then finding where it's positive and negative. So f prime will be 12x cubed minus 12x squared minus 12x plus 12. Find where the derivative is 0 first. Well, I see that I could factor this by grouping, so I'm going to group the first two and the last two and take out common factors. So 12x squared times x minus 1 minus, now I'm going to take 12 out of the next one, 12 times x minus 1. Now factoring out the x minus 1s and the 12s, I'm going to get 12 times x minus 1, and I'm going to have left an x from the first term and just a 1 from the second term. X squared from the first and 1 for the second. So now I'm going to have 12 times x minus 1 times x minus 1 times x plus 1. Or you could write it as 12 times x minus 1 squared times x plus 1. And that's the derivative. Okay, draw your number line. Get your critical points. My critical points are going to be what makes the derivative 0 or undefined. The derivative is 0 when x is either 1 or negative 1. The derivative's never undefined. Okay, put those numbers on the number line. So I've got negative 1 and 1. They just divided my number line into 3 intervals. I've got the interval from minus infinity to negative 1, negative 1 to 1, and 1 to infinity. Okay, so now I want to check the derivative in each of those intervals. So I'm going to pick a test point in each interval and find out is the derivative positive or negative. Now the derivative I'm going to use is this factored form because it's going to be easier just to determine whether it's positive or negative. So I'm going to put in maybe -2. I'm just going to pick something in each interval. So I'm going to find f prime of -2. When I put -2 in for the x's, I'm going to get 12 times -3 squared, which will be positive. The 12 was positive, and -2 plus 1 is negative. So I'm going to get that this is actually a negative number. So f prime is negative here. Pick something between -1 and 1. I'm going to pick 0. F prime of 0, when I plug 0 into my function, I'm going to get 12 times -1 squared, so that's positive, times 0 plus 1, it's going to all be positive, so that's greater than 0. So f prime is greater than 0. And now I'm going to pick something in the interval from 1 to 0. And I'm just going to go ahead and just pick 2. So f prime of 2, put 2 into your derivative. I have 12 times 2 minus 1 squared is positive. 2 plus 1 is positive. This is just going to be positive. Okay, so what I have now is I know where my function's increasing, where it's decreasing. I have that the derivative was negative from -infinity to -1. That means the function's got to be decreasing. Between -1 and 1, the derivative is positive, so I know the function's got to be rising. Between 1 to infinity, the function is still rising. Okay, I did have that the derivative was 0 at -1 and at 1. So now my possible maximums and minimums occur at the points, the critical points where I put them on the number line. So now which ones, what do we have there? If you look at -1, we had that the function was falling to the left and rising to the right. We know we have to have a local minimum at -1. So I have a local minimum at x equal to -1. At x equal to 1, I see that to the left of 1, the function's rising, but the function continues to rise after that. So at 1, I have no absolute, no maximum or minimum, so no extremum. Okay, so let's see, what were we asked for? We were asked to find the intervals where it was increasing and decreasing. Well, increasing was on the interval from -infinity to -1. So decreasing was on that interval because I see that the derivative was negative. On the interval from -1 to 1, I see that the derivative was positive, so I know that the function had to be increasing there. I also see that from 1 to infinity, the function is increasing. Now, -1 to 1 and 1 to infinity are both increasing. We can put that in one interval as long as x equal 1 is in the domain. Is 1 an allowable number into this function? Is it in the domain of the function f? It is. We would get a y value there. So we can take these two intervals and combine them and say that it's increasing from -1 to infinity. Okay, and it was decreasing from -infinity to -1. So those are the intervals where it was increasing and decreasing. Our extremum, we had a local minimum at x equal -1, and we had no extremum at x equal to 1. So the only one was at x equal to -1. Okay, I want to find the local extremum of this function. Okay. First, we need to find the derivative, f prime of x. Using the product rule, we're going to have x to the 2/3 times the derivative of 2 minus x, which is -1, plus 2 minus x times the derivative of x to the 2/3, which is 2/3 x to the -1/3. Factor, I'm going to take the negative x to the -1/3 out. Okay, and so I'm going to end up with a negative, just a single x to the first power for the first, because if I multiply these two together, I will get x to the 2/3 when I add the exponents. And then I'm going to have plus 2/3 times 2 minus x. Okay, so adding the parts in the bracket, I have negative 3/3 x plus 4/3 minus 2/3 x. Okay, minus 3/3 x and minus 2/3 x will be minus 5/3 x plus 4/3, and I have that times x to the minus 1/3. Now I've got my common denominator of 3 here, so this would be just minus 5x plus 4 over 3 times, and then I have the cubed root of x on the bottom. Okay, so now we need our critical points. Those are the numbers that go on our number line. Okay, so label our critical points. The critical points are what makes the numerator 0, which is where the derivative is 0. So f prime of x is equal to 0 when minus 5x plus 4 is 0, or x is equal to 4/5. F prime of x is undefined when x is equal to 0. Put those on your number line, so 0 and 4/5. We now split the number line into 3 even pieces, or not even pieces, 3 pieces. So we're going to look at the intervals from minus infinity to 0, from 0 to 4/5, and from 4/5 to infinity. Now notice at 0 that the function, the derivative didn't exist. So f prime does not exist. At x equal 4/5, we know the derivative is 0. Okay, so now we're going to pick test points in each of those intervals. So I'm going to pick maybe -1 in the interval negative infinity to a 0. If I put -1 into this function, -1 to the 2/3 times 2 minus a -1 is going to be -1 to the 2/3 is the cube root of -1 is -1 squared is +1 times 3. So that's going to give me 3. Okay, so that's f of -1. I think I need f prime though. F prime of -1. Let's go over to f prime of -1, and I'm going to get -5x plus 4 over 3 times the cubed root of -1. Okay, so I'm going to have 9 on top over -3 on bottom, so -3. So that'll be my derivative. F prime then is negative. Again, you don't have to look at the exact number, just get the derivative sign, whether it's positive or negative. Now between 0 and 4/5, let's just pick 1/5. Find if the derivative is positive or negative. F prime of 1/5. I'm not going to worry about the numbers now. -5 times 1/5 is -1 plus 4 will be positive. So I'm going to have a positive on top. 1/5 into the cubed root will be a positive number, so I'm going to have a positive number on the bottom also. So I see that the derivative here is positive. Okay. Now for something bigger than 4/5, let me use the number 1. Look at the derivative for when x is equal to 1. F prime of 1. Now the top, when I put 1 in, is going to be a negative number. The bottom, when I put +1 in, will be a positive number. So I know my derivative then is going to be a negative number. Okay. I want the extremum here. I'm not even asked for the intervals of increasing or decreasing. Just looking at where the derivative is negative. If the derivative is negative from negative infinity to 0, I know the function's got to be falling. From 0 to 4/5, the derivative is positive, the function is rising. And from 4/5 on, the function is going to be decreasing again since the derivative is negative. So now looking at where the extrema occur, I have an extrema that occurs at 0 and at 4/5. But I need to make sure those are actually points at those places. 0 is a valid element in the domain. If I put 0 in, so f of 0, I don't care about the -1 up there, f of 0 will be 0 times something else, so it's going to be 0. F of 4/5, I really don't even care what that number is unless they ask me specifically for that value, but if I put it in 4/5 to the 2/3, and then 2 minus 4/5, so it's going to be 6/5. Okay, that's the y value that occurs at this point right here. Okay, now the derivative is 0 there, so it's going to have a horizontal tangent line. Now the derivative doesn't exist at x equal to 0, but we do have a y value there. Okay, so what we do have is we have two extremums. We have the local maximum at 4/5. And if we wanted to put the point, we know the x is equal to 4/5 and the y would be whatever that 4/5 to the 2/3 times 6/5. So the local maximum at x equal 4/5. And we have a local minimum at x equals 0. Now, just pay attention to what they ask for in the homework questions, because they may want the y value. The local maximum is actually the y value, so it'd be that 4/5 to the 2/3 times 6/5. The local minimum would actually be 0, since that's the y value, and it occurs when the x is 0. Okay, now if you wanted to see what the graph of this, if you plotted this on your calculator, it looks something like this. It's coming down, it takes a sharp corner, and then it jumps up like this. So here's the point where we have that local minimum, and here's the point where we have that local maximum on the graph. Okay, now one more example. We've talked about absolute extrema and when they exist. We know if you have a closed interval in a continuous function that they definitely exist. But this says that you're going to have absolute extreme values on any interval under certain circumstances. Okay, this says that suppose f is continuous and that it contains exactly one local extremum. That means that you've got this one local extremum, that's the only one. So that means that it can't go up and curve back around, or you'd have another extremum right here. So what's happening is it has this one low point, but then it's going to keep going. So what that means is that it's actually got to be an absolute minimum also, if that's the only local minimum or local maximum. So if there's exactly one extremum, one place, one turning point, one place where that derivative is 0 or undefined, then it's got to be an absolute. So if it's a local minimum, then it's going to be an absolute minimum. If it's a local maximum, it'll be an absolute maximum. So this is only applying, though, when there's exactly one local extremum. So let's look at an example here. Verify this has an absolute extreme value. Well, let's find the derivative first. The derivative would be x cubed minus 3x squared plus 3x minus 9. Factor by grouping, I'm going to have x squared times x minus 3 plus 3 times x minus 3. So I've got x squared plus 3 times x minus 3. Okay, my only possible extremums can occur when this derivative is 0. There's no places it's undefined. So when x is equal to 3, when that factor is 0, now there's no x value that would make x squared plus 3 0. So the only critical point is at x equal 3. So I can't have but one extremum. Let's check it just to be sure. That's the only place it can change. So at x equal 3, pick something to the left and the right. So let me just pick something simple. I'm going to pick 0 on the left. So On the interval from minus infinity to 3, I'm going to pick x equals 0. Put 0 into the derivative. 0 in here is going to be positive here, negative here, so I know that f prime is actually negative on that interval. If I pick something like x equal to 4, plug into the derivative, x squared plus 3 is positive, 4 minus 3 is positive, I know that the derivative is positive here. So what I've got is I've got the functions decreasing to the left, increasing to the right. I have exactly one local extremum. It's actually a local minimum because it's decreasing to the left and increasing to the right. So I have a local minimum at x equals 3. And I know it's got to be also an absolute minimum at x equals 3. Because it can't turn around again if that's the only, local extremum.